Here we go. Are we live? The tilted camera means there is action. I don't know what kind of action, because I didn't achieve much since last time. Can't hear anything. What? Why no reaction? So, where's my sound? Is it broken? Broken again? The TTS? Damn it. Yeah. I did some gardening, that's why I wear a dirty shirt. That was the only day this week where it wasn't raining all the time. So I had like to mow the lawn. Mow the lawn. This is difficult language. TTS is broken. How unexpected. Yeah. After this project we take care of the housekeeping and improve on that. I don't know what's going on. Why is it dead again? Let me trigger again. That's the stream name. Hello lines and squares. Hello Christian. Hello Dutch. Hello Wagon. Hello Johnny. Hey Johnny. Okay, so yeah, I have to work with what we have here. So I will start my own server with blackjack and hookers and demonetized. Here we go. I have some. Wait, that's the wrong one. 5,500 is TTS. 500 and then chat HTML. No. Fuck. Go live. Okay, let's try. Okay, here we go. I hope this works. Hey Ray. Hey Anna. Wow, we have some people today. Hey TMK. Hey I'm a Boyd. Yeah, I don't know if that works with. I can't hear anything, or is it? Am I mute for some reason? No. Ah, okay. And that one works. All right. So since last stream, I thought, well, I can use the plot to basically show where I detected or the start of a packet and stuff like that. For your information, if you're new to the stream, here we go. Okay, we have this small cassette, micro cassette recorder that I stripped down, and it yeah, I can show you. Where is it? How do you? Yeah, this is how you open it. There is a micro cassette, and shoot, it's hard. I don't want to rip off everything. Close it already, and it's broken. Wait, is the lever down? Yeah. Huh? Did I press on the lever here? Oh, I need to disengage. Yeah, like that. Okay, here we go. All right, so oh no. Oh yeah, I ripped off this wire, but it doesn't matter. This is only the speaker, so we won't have any audio anymore. We will only, yeah, this is the board that will fit sandwiched in between here. And now I can reveal what the goal is. Let me show what the goal, what we are building. What? Stream isn't over. What's going on? Okay, so what we want to build is this here, but a little bit smaller. Here, this is the size comparison. This is the size comparison, little smaller and USB based, with the turbo loader von Ducam. I show you what I even bought. I spent 60 bucks on filament of the right colors. We can open this up because I bought it from Bumble Lab because I had really problems with the crappy one. This is PLA in silver PLA. So this will be for the front plate here. This is the silver. Then we have black. I ran out of black. That's just matte black. The matte black is for the matte black part. Commodore. The buttons aren't black. They're brown. You can't tell probably why this bad. So we have only this part is black, framing and maybe button if I do that. Then we have beige, beige in German. So I hope that matches. Yeah, looks quite similar. We have beige, and then we have brown. Shaliko, I mean, so yeah. So this is brown for the buttons. The buttons will be fake because there is nothing to do with the buttons except for the eject button, and I need to discover some mechanic for that. But as you can see, brown maxed out. Yeah. 60 bucks. This is what I do for your entertainment. By the way, I bought brown. Is it too loud? Brown. Oh, it maxes out. What is going on? Wait. I will scale down. Okay. I 3D print blend colors to get other colors. You could, but okay. I don't want to. Pink LED button. Look at this. I got this. I think for 20 bucks. I was missing controllers and cassette part for my Commodore, so certainly some more Commodore stuff is coming. I just needed this device. I don't know even if it works. Never tried. I don't even have a cassette which has stuff recorded on it. eBay. I can show you. eBay, and there is more. You can buy like a used device for 20. A new one, even with packaging, you can buy there. Wait, let me show you. There are other ones in worse shape, probably, and let me check. I want to dox myself. Here. Oh, wait. Did I pay 40 bucks? Okay, I might have paid 40 bucks, but I saw one for... Oh yeah, it's 30 bucks plus shipping. 32 bucks plus shipping. Here we go. Show you it here. With the controller. So a used unit, this is one in a good shape. There are with terrible shape and other coloring. Apparently there is like differences. You can buy, if we search, yeah, you can, yeah, starting from that. This is, wait, let me do just only yeah, the black ones. Is this black or brown ones with gray buttons? I don't like this style. This doesn't look original to me. This is how it looks, like yellowy. Oh, this is broken. This is like really odd Oh, that's a Kühlschrankmagnet. So it's a magnet that looks like a dataset. There's plenty of different ones. Do you see, like uh, uh, with original packaging for 50 bucks? Here, 30 bucks. You can just buy it right away. Here, 23 bucks from Britain. If you're in Britain, you can get one cheap. Or here, yeah, but this is broken probably. No Ersatzteile. So only replacement parts. Look at that. It looks like it's new. What? Is this originally? This is only like fake originally packed, but it looks unused. This is like mint. This is mint condition, peeps. 100 bucks. So no worries. Holy moly! Yeah, that's not much, I believe. Yeah, I watched that video. That guy bought the Commodore rights, and are they the same that selling the new Commodore like remake? Now that he got the rights on the trademark. That's really cool, I must admit. So, Fox Retro Player. I wanted to show you what I did in during the train ride. I started already, since you're like CAD serious CAD stuff. Where is it? Here. I will show you. It's loading. Is it loading? Yeah, it's loading. Here. Oh, I think it's rendered. No. Okay, solid. It doesn't. It's same depth, so. But this is basically what we are aiming for, and width is around, what is it, 6 centimeters? Let me check. Yeah, 6 centimeters long, and let me move that down a little bit. Here. I just took, and this is like, you can see it lacks quality, so I might need to take another. I used Inkscape to get from, and basically I can use a scanner now, because I didn't get a flat image of the device. Now I can get put it on the flatbed scanner and scan it, and then get the vector lines. Excavator! Ooh, Johnny, thank you very much. I will instantly put it in the excavator fund. Sheets. Excavator fund, 100 SAK. How much is that? 10 bucks, is it? Let me check. Let's ask. Oh, €8.95. €8.95. That's 100. 100. Johnny. Only 10 years. In roundabout. We are 2.2%. That's like, we started a month ago, so extrapolated, we get like 25% per year in 4 years. Excavator, and 48 months. Maybe earlier because they get cheaper. Maybe I can get a unit used. Used unit, or I get a deal because that's like from a regular hardware store, and sometimes you get like a coupon 10% off in the hardware store, and if I can grab that coupon and buy an excavator, they will make big eyes. A gotcha moment. Turmbaumarkt. No, what was that was Hornbach. Hornbach Coupon. Oh! Yeah, here you go. Rabatt code. Yeah, this is probably not Hornbach's Rabatt code. Here. What is it? Extra 10. So that's 530 euros that I can save. That's a lie. Yeah, probably. Yeah, but sometimes we get like hey Casper. Sometimes we get like prospects or like brochures where there is a coupon, or if you have like a sale or whatever. Yeah, we are intro part where I showing Caspar. You missed that beauty. I'm. This is the design, 6 centimeters by 5 centimeters. Here. Let me select this. Yeah, 5.5, 6 by 5.5, but 3 centimeters high. The thickness, we can't do anything about that because the PCB and the device itself is so thick. Compared to that, let me get the PCB that's basically the size. Here. This is the size comparison. This is the PCB. The device is slightly bigger than the cassette, and this will be similar capabilities, hopefully. Small, yeah. Yeah. Yeah, that's awesome. I really wanted the original colors, and Caspar, you missed that. I bought for 60 bucks. I bought all the filaments that I needed, like the silver, black, beige, and brown. So, fuck. Okay. And demonetized. So this is now it's revealed. The goal is revealed. By the way, I did a little bit of tuning since last stream. Let me show. USB only. Everything USB. So this is already, if you look at huh? See? Show me. Here. So this is already only powered by USB. This here is because this cassette recorder works with triple A battery, a DC to DC buck converter, takes the 5 volts from USB. It needs like half an amp or something. TTS only working on my PC I'm using. Somehow it doesn't work, and I don't know. For some reason, it acts up today. I'm using my local version to hear you at all. Sorry about that. You need to read. We will take care of that after this project. So, what I think we will do. A side quest here. I think you will like it. If you didn't unfollow and abandoned me because I did a sponsorship with BetterHelp, then you might like the future. What I think I will put on my website, I will put all the videos, so my website will get a remake. So you can stream the videos on my website without any ads whatsoever. Like the latest video, no ad, no mid-roll. The same thing that might be mid-roll, might be the sponsorship. If I get more views there than on YouTube, then probably fully funded by supporters. But also, what we will do on the website is live streams will be there, including TTS built in. TTS, and you can switch it on. Boop! And you can watch the embedded video if that still works. I hope that works. With TTS, and hopefully also embedded the chat. I don't know if that probably will work. Yeah, so that looks like Illuminatis. Yeah, but yeah, better experience than shitty sites where you don't have options and whatnot. I don't know. I think I will be like it's a simple site. I mean, you just need an iframe and embed the stuff, and then the TTS runs in this chat already here. So that works perfectly fine with Chrome. So you can use basically even, I don't know, you can basically have the TTS locally, and we don't need the Discord anymore, which X up every time with bitluni. Although I liked bitluni a lot, and that might be easier this way. Anyways, back to the topic. Back to Chopper. Where are we? Wait. Oh. Where's my window with... Here we go. Okay. It's my debugging window. I show you one. So I did a few things. One easy thing to see what we actually receiving. I changed a few things. I'm using the actual, not square wave, because I noticed on higher frequencies we get some overtones and like jiggly lines. And yeah, this is true sign. And this lower frequency is 1.5K, and this is 3K, and it somewhat works. If you can see, we get 0 to 8 correctly. Unfortunately, from there on we get a drift. I didn't fix the sync yet, but there is a nice feature. So I can move basically, and we will see it clears also the output. Wait, where was this? Here is a start, and there you can see if it found the sync or whatever. I can move that. Oops. And once I get in the No, doesn't work. Okay, sync and decode. Okay, this one works. I thought it will. It doesn't. Probably broke something. Anyways, this looks promising. I just need to adjust from byte number 8. It's not even visible on the screen, so it looks all right. It could be like a little bit more to the left, but we get like here the zeros and ones nicely in. This looks very good, and it deteriorates here somewhere. Doppler shift. No, but this is the thing. What we doing now is maybe this is also a recap. Okay, Illuminati gone here. Where's the cursor here? We have, by the way, the signal is inverted in the output. It's strange. I don't know. I don't know why, but playing back, the polarity is inverted of the signal. So even though this is like positive, we get this signal here. So with our detection, doesn't matter because we take like the absolute values or a quadratic value. So what we have, I changed it, by the way. So the first bit is a 1. Yes. I switched it from 0 to 1, unlike in UART, because 1 is the lower frequency. And especially in the beginning, from silence on, the swing in takes a lot of time, where, this is then the higher frequency. Whoop, 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 whoop. And this is our 8-bit, so 8-bit. So we actually know. Hey, Coolpad. Hey, okay, Scylla. Did I miss anyone? Wall, yep, hello. So we have like this pattern that we can basically match. Oh, it's the tone. We are frequency shift keying. It's called FSK. Fan spin. All right. So what we are checking is we check for the match of the start stop bits, which are these values here. And this gives us, it's working again, what? Oh yeah, you mean my impression. And basically what we get is from checking the start and stop bit, from the start and stop bit, we can, every single byte, we can check if the prior or posterior, is it posterior, prior, posterior sample returns a higher match with start and stop bits. So each byte we could move one sample back and forth, previous and not quite, because the full size tape does it is actually the same format, but not with start and stop bits, I believe. There is like different data packing, but frequency shift keying is used. What they do is quite simple. they count only like in a certain amount of time. They count the passes through zero. So in this case, it would be 1, 2, 2 passes during the time frame, and this one will be 4 passes. So 4 is a 0 and 2 is a 1. This is how the C64 does it. But this, we could do it, or we do it difficult way like we do it right now. And then we can measure the power and can copy full-size tape to the mini. Maybe. If we would replicate the same frequency and everything the same, but I don't want to do the work, to be honest, because I have to read up stuff and so on. Anyways, we can calculate this. This is like quite simple. We can calculate it by, this is 1, 2, 3, 4, 5, 6 additions, like, or 5 additions and 1 multiplication to calculate the power of one sample. And if we do it 3 times, then we can determine if the match is like, if we have to adjust the position in our stuff here. So let's implement this first, and then let's care about other stuff later. Where is my code? Here is the code. Wait, this is the wrong code. Too many codes. Here. All right, let's implement it in here. I changed the code a little bit. Sorry. Find sync basically looks for the first synchronization. Oh yeah, it plots out. Wait, I can remove that. Start. Yeah, that sets the start marker. And this is what does the decoding. And then we can do adjust the raw position. We can do like check sync, or this is find sync. Yeah. Get byte frame power. This is what we do, and then we do like that. Let's do this here. Let P 0 equals that. We just check the samples like that. +0, +1. We could do a loop and test it afterwards, but you know what? Let's do it. For displacement, so let displacement be 0, or is it adjust, or how do we call it? Or max, not error checking, but we try to fix the sync if it's shifting. Like if we have a different frequency. I noticed we had a shift before at 1 kilohertz. I noticed a shift by around about 0.5%, 1 to 0.5%. So there was like the signal is deteriorating. If we can fix that, like max power and max J. Let's do it like this. If P is greater than max P, then do that. Why does it not put in the right space here? Okay, max P and max J equals J. And then afterwards we can fix it by just using I plus plus equal J. We probably be, if we start at the beginning of the array, it might be out of bounds, but this is how we can adjust the sync. So this decoding assumes we have sampled already the 320 samples. We have 32 samples per bit, and we saving start and stop bits. So we have 10 bits, that 320. That was one of the errors on the at the end of the last stream, that I didn't check the right sample size. And now we have the adjustment. I just need to oh yeah, F2V chip, yeah. We can do this in post. We can do this all in software. If we can, like, if it would be like perfect offset or whatever frequency during playback and recording, then we could just find that. Or at the beginning of the playback, we could actually find the right frequency using FFT and or whatever, adjusting our frequency back and forth to have the perfect sampling rate at the end. But oh well. We do it like this. That's start, and then we just do the same what we do here. Super easy. Super easy. We know what we want, so yeah, const, whatever. The start of the thing, so this is at 8, and this is then 1624, 8 and 24, this is correct. But then we need to consider also, this is the start bit 0. Then we need to, yeah, we can copy that and then add the stuff. The only thing that we need to consider is the quadratic at the end. Okay, so this is 320 minus 32. Because I'm lazy to calculate. 288? Is it 288? Yeah. Okay. So this is, oh wow. Stop bit 0. Oh, wait, this is 0. This is 1. Here. Start bit 1. Stop bit. the B flipped downwards. Stop bit 0, and then we return. I feel rejuvenated a little bit. I spent a lot of time lawn mowing today outside, and it wasn't raining. I feel like the weather is pulling me down. I hate this weather. It feels like we are betrayed of our summer again. The winter was so long, and then June and July completely rained. I hate it. We have 20 degrees C. We have like for sleeping, we have like a thick winter blanket and a thinner summer blanket. And the summer blanket is too cold currently. Too hot? What? Wagon loads! Where are you again? I want to be there. Okay, should we test this? This looks like it might work. Okay, retest. Oh, we didn't connect yet. Here we go. We won't hear anything because I ripped off. Ah, USA, nice. Okay, sync and decode. Oh, it's broken. It's broken. What is the start? Oh wait, I didn't put the start at the beginning. Shit. Okay, yeah. Let me. Sorry. I will use the P there, not the start. P for position, not for power. Here we go. Connect. We got only. Okay, here we go. Oh, it's that again. What's going on? Huh? Huh? Oh, J is not oh, Max J. That's stupid. Okay. This is what happens if we don't vibe code. Stupid person mistakes here. Here we go. Max J. Alright. Third try is the charm, isn't it? Or how do you say it? Oh, that's read ADC retest. Okay, start the code. Yes! What did we get? Oh no! Oh no! It's that! Ah, sync didn't work. Wait, this doesn't matter. But why is it so broken? This is correct. This is correct. This is correct. 5 is wrong. Completely wrong. Shoot. My super fancy sync technique doesn't work. Maybe I should skip the first byte, because that's the sync byte anyways, and it's totally skewed. Let me decode. Minus 64. Oh yeah, plus 360. So start 320, skip sync byte. Because the sync byte, you see, this is like not looking very well here. It should look like this, but it's only like that because it's in the start of the recording. I'm wondering if it would be smart to, before we do the silence, doing something else there, or a completely different frequency. Was also suggested last time. Okay, let's reconnect. Oh, not read ADC, retest. Okay, decode and sync. No, that's shit. That's shitty. It's worse than before. Huh? Okay. Let me check that. If we can get a better result without without my correction. Maybe my correction is wrong. Oh, it's different because no, because we no. Oh shit. Now I screwed up and started the recording test. Now we have to wait until it recorded a pattern. We also don't get like the right block. Oh, by the way, I need to fix that. So let me check. Decode, find, sync. Okay. Okay, retest. Here we go. There is like some overtone here. Oh no. Without correction it's better. What? It performs better without the correction? Am I correcting in the wrong direction? Huh? Yeah. I'm wondering. Oh wait, that's the wrong thing anyways. So let me check that. We start at J, max J. If P is greater than max P is P. Oh. Okay, that's on me. Now it will be perfect. Oh no. Where's... Here's our... Nope. Wrong. It's worse. It's worse. Hey Marcos Kakos. Too much AI code. It's completely not non-AI code. Okay, let me try again. That one breaks at this number here. 188. How many numbers do I store even? Let me check the code. I'm using the recorder and generating an audio signal. But you know what? I would need to see the corrected version here, because I'm displaying the wrong stuff. Oh, that's not corrected. Look at this. I removed the correct. Now the correction. Now the correction is coming. Now the correction is coming. Here we go. Nope. Breaks. Fuck this. Damn it. Sorry about my... This is getting annoying. Maybe we should take like two waves that halves our data density. Not even the correction does the job. Okay, let me try more correction. What is the maximum shift that we would be able to compensate here? It's also quite skewed. It looks like the bottom peaks are sharper. Oh, nice! Congratulations on that. Okay. Yeah, we'll try again with better correction. Yeah. 0. Oh, 1, 2, 3, 9, 8, 0, 0, 0. Shoot. That doesn't look like it's correct. No, it's frequencies. Lower frequency is a 1, higher frequency is a 0. Two different tones. What I could do is I could double the sampling, the frequency, not the frequency, the waves to... We can try that. I hate it, but we can try it. Okay, so encode. Encode packet. Ticks per wave 20. Yeah, let me check that. Get time. Okay, times 2. times 2. That should be it basically. Ticks per wave. Get time. Yeah. That should be it. Now we need to slow down. No, make fewer samples here. We only counting to 16 anyway, so any number higher than 16 shouldn't be returned. Yeah, it's, I don't know, the sync is missing. It's hard to tell. That's the issue. What we could do, we could try a completely different method by counting the peaks, like when the audio is flipping the direction downwards, and then count that. Or we maintain the 0, but no, couldn't tell. It looks perfect here. So this is actually spot on, the sync. And it deteriorates after, in this case, 4 bytes. And we weren't able to recover it with start and stop bits, which is quite annoying actually. I don't want like more sync bits. What is UART? No, that's the decoder. The decoder, if the signal was perfect, the decoder would be nice. But we are working here with analog stuff, so I'm not writing like directly. I'm using like audio. So we have some noise in the background. Then we have like swinging capacitors and inductors. Like the writing head is an inductor, and then you see something like that, which actually indicates that we are aiming too high, because the center of the audio seems to be too high. As it overshoots and then recovers. This is strange. Why does it overshoot in this direction? We might want to check our DC offset, because I'm trying like to write with a certain DC offset, and if the DC offset is bad, then we shouldn't use it. That might be confusing. We can already see here it's quite tight. Maybe I will do, let's try this first, and then reach sample buffer. Yeah, I hope it's enough. Okay. I'm using currently, we tried start and stop it like UART, and fixing the sync by matching that few samples back and forth. Didn't work. Didn't improve anything. Now I will try to use 2 waves per bit. So let's connect and do the record test. Now we will wait. Foo! Is this excavator fund? Thank you very much. 4,000. Where is 4,000? That's like 95 cents. 95, and it's full. Okay, it's rewinding. Now we will see. We can play it and see. We can't hear it, but you can see this is what we get. Okay. Let me rewind. Come on. We can deactivate that, and then we will do a retest. Percentage, yeah, we have the percentage here, 2.26%. We calculated it will be only 4 years to get it funded like this. So I need to. Oh yeah, by the way, this can't match. Yeah, it wasn't visible. We need a new, since we have now multiple swings per thing here, we need to test that as well. So 640 is now the thing. 640. Let's not correct anything. I will check if that works. 640. 640. This is all right. Oh yeah, we need to check now for this frame, byte frame. It doesn't need that. Raw position, find sync. And this is what we need. We have double the things. 32, that's 40, and 60, 56, and this one as well. We don't need to adjust it because this frequency is lower. Lower in power or amplitude. 32, that's 36. 44, that's 52. And this is 32, 60. Okay. Cup holder. Thank you, Dusty Circuit. 50 SEK. Circuit, and we have 50 SEK. That's 0.48, and let's round up. Thank you very much. Okay, so I hope this is correct. Oh, times 64. Here we go. Connect, retest. Okay, sync and decode. Nope, not better. Still losing it. Doesn't do anything. Why though? Why? Wait, let me also show. Wait. Oh, you don't know the excavator font. First rule about the excavator font: we don't talk about the excavator font. I need to. So it's a stupid font where I get this mini excavator to do my to do my terraforming project in the garden. It costs 5k, yeah, 5.3k, and we are collecting for that. Here, copy link. I should put the link also in here. Here. Why are we struggling so much with this tech? We should just implement this stupid method the C64 is using with the Schmidt trigger. Just counting the zero passes. But how do you count the zero pass when you get a skewed signal? Wait a second, I need to fix something. Boop. What? Oh, really? Then I got it wrong. Wait. Yeah, you're right. 448, yeah. 485. No, 75. Sorry. No, 447. Sorry. DC drift detector. Yeah, I can do that. Thank you for this is very generous, Dusty. Okay. I wanted to highlight start. But this is stupid. Connect. Oh. Yeah, that's quite off. It should be rather here. Here. No, here. This would be, there is some drift, but this would be the perfect match. A slight drift here. Yeah, here already it drifted a lot. Why did it detect it here? Okay. Let's make it more sophisticated here. Get frame power, get sync. Didn't improve anything. Squirrel where? This decode byte. Complementary pairs. Yeah, I have no stereo, sorry. That would be amazing though. Ah. Is there something similar to that? Second half of the bit? What do you mean? I mean, in that case, this is like two swings of the lower frequency is a 0. Then we have 4 swings of the higher frequency, which is a 1. The only thing that really confuses me is that it goes down there. It's like this Q down there. Maybe we do not a simplified but a proper decoding here, like with sinus. Phase. Oh wait, position. Okay, we need raw for '64. This must be always seen as math. Sinus. And then we have pi times 2 divided by 32. Times J times raw P plus J yeah. There is certainly a DC bias. During the recording, I can set, like use, yeah. So there, we might want to try different DC offsets, but that's like a trial and error. We could try to see if we can lower this deviation, but we are also working at the limits of the tape, basically 1.5 k. The lower frequency is 1.5 kilohertz, which is already yeah. I don't have stereo. Waggle nodes. I would need like 2 write heads or read heads for that. So I can't do that unless I put it on a different frequency, completely something different. P1 equals P0 equals and then we have this is not needed anymore. Oh. We will try edge detection next. Pop. This is the lowest power. This is also a thing that I changed that we might want to change as well. Okay, let me try that first. This didn't work. Is it out of scope? Damn it. Do we have? Damn it. Where's the 0? Let me try to find 32K. It's the samples that we got. Oh, look at that. Why did it? Here. Shit. Here is the start. Why isn't it detected properly? Oh, wait a second. The power is way too high. Yes, mid trigger. That's how the original device is doing it. By the way, I found there is a clear console clear to clear the console. That's really helpful. Oh, this is slow. Why is this showing source? Why is it showing find sync? Huh? It's not updating? Clear console. I don't know. Huh? how I find sync, input, oh, input, find sync, okay. Does it calculate the sync again? Sync power, decode byte start. This value times 1 maybe. But why does it? Why do people not know their easy island? Here we go. What does it? Yeah, it's a string. That's why it's confused, my friends. That's why it's confused. Let me try again. Now with the fixed code. Boop. Sync the code. Okay, we need to check what is the value of that we get there. Two 5. That's what we are looking for. 2K and more. Okay. Also, I didn't fix where we find the silence. Oh wait, I didn't check that. Why is it detecting a 0 here? Oh, I need to debug everything. First of all, the power of sync needs to be 2K and plus. So let's do 2K. Then we need to find out, you probably want to see it as well, decode why it stopped decoding here, decode byte. Why did it decode? This is the first byte. Okay, let's check it here. So this is certainly a 0. Okay. A 0 again. Zero again. 0, 0, 0, 0. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. It's always 0. Yeah. I found one issue. How about a plus here? Okay, let's fix that. Aha! Fuck! Nine. 1, 2, 3. 1, 2, 3, 4. 1, 3, 1, 1, 2, 3, 4, 5, 5. This is getting worse by the minute. This is getting worse by the minute. What is this crap? This is worse than before. 5, 6, the 4 is not detected. 7, 8, 9, the 1 is not detected. It's 0 is overrepresented somehow. It's overrepresented, the 0. If we sync and decode, it doesn't even like sync and decode properly here. This is also going on my nerves. Let's try doing that. Not the minimal power. The minimal power will be something else. We will test this another time. Oh shit, I pressed the wrong button. Okay. 128, 3, 2, 3, 4, 15, 15, 15, 190. And we get ridiculous power here. Ridiculous power. Quadratic power is sick. Because we are not checking the minimum. Maybe the minimum was better. Okay. Let me try. Let me check something else. Yeah. Let's do the. Let's do a lower frequency. And then later, let's do 1K. That seems to be the sweet spot of this device. But we might get some wrong stuff there. I expect more noise on. On the lower frequencies. Oh no, we have a really long recording phase. I would really love to see this wave look like more like a sine wave. It looks jagged and I mean, I'm probably expecting too much, but why is this overshooting here? Maybe I should do a lookup table with wave shapes. Yeah, they don't look consistent. But what if I have a lookup table with a wave shape which played back looks like the actual shape that we want? That might be the approach. Let's fix the waveform while recording and wiggly. Okay, retest. Need to play the silence off. Whoop. Ooh. I'm using a lookup table as sinus lookup table, but not the really. Yeah, for sine I'm using a lookup table, but we need something else than a sine. Something this looks like almost perfect sine except for the corners at the top. Yikes! Why is the sync so bad? Let me fix the sync for you. This should be the sync. Nah. Doesn't work. Wait a second. Am I wrong? Is this what it's supposed to be, the actual sync? One, two, three, four. Yeah, 50 Hz, that's probably not it, no. Because this is... maybe. $50 is way lower. Wait, I need to reload that. We changed the minimum. Boo. Let me check. What if the sync is this? 0, 7. Then it deviates. This would be 20K. Huh? Didn't I fix that? Define the sync stuff. Decode old, decode byte. Where's the find sync? What was it? 40, let's do 30k here. Let's try if it finds. This is what we are looking for. No, it's also not right here. It's there is a lot of shift. What's the highest number? Has sync power is only $1,300, 5,000. That might be the case. 200,000. Okay. Is there a systematic error? Okay, we have 30,000, 150, 56,000, 300,000, 500,000, 500,000 now. This is the quadratic stuff is this is way too explosive. $100,000. Okay, connect. Nope. $600,000 is the best I can get. 3,600, 400. It's interesting. We get like the negative. We should maybe also consider not changing the sign here. So no power at all. How about this? Because we know in which direction the wave should go. If we shift it by half a wavelength, that might be bad. Ah, didn't find it. Oh, wait. Let's see what kind of value we get here. More like 800, 500. Okay, this is what we are looking for. More than 500. Okay, let's try again. Now sync and decode. Okay, that looks... yes, but we do something else. There is like this AC, it's AC coupled, and we also get AC voltage back, which we shift here. So we can, I can only... Oh yeah, we can probe it, maybe. Yeah, that would be a thing. And yeah, we should probe it with the scope. Huh? Usually when we do that, let's see, I rewind, you can even see a shift in DC, but I don't see it right. Do I play it? Huh. Oh, we should see the, we should also output the decoded thing here. Retest. And then sync and decode. Oh. Huh? Didn't I reload it? Oh, here we go. Yeah, it only got the first values right. And then everything fell apart. Which is really odd. I'm wondering if we add our correction now, what does it look like? Sync decode. That what we get from the tape is something different what we input regarding the voltage. So I can see there is like a slight shift here. Yeah. Look at that. We lose our sync even though I try to fix it. Minus, why is it minus here? Sync is 800. The first is... Okay, let me check. Where is it heading? 500. Now it's deteriorating here. Yeah, this is already too far shifted. 5. Oh, look at that. If we move it by 1, every, like, it looks like the samples are shifting here. Now we get 7, now we get 8, now we get 9, 10, 11. It looks like our sampling speed is too fast, but our correction should fix that. 14, 15, and then it's gone, because we only store 15. So the data is there, it can be decoded, but the window needs to move slightly. And I thought this is what we are doing here. Wait, let me check again. Okay, sync. Now 3 is improving. That's like +2 per byte. Okay, first byte, then second byte gets. Can I remove close that window? I don't need that window anymore. Close the filters here. Okay, now you can see what I mean. Okay, I move 1, the sync +1, then it improves. 3, 4. It constantly improves. It's so strange. Our shift method should be working. Hey, Christopher. Only by 1 frame. I don't get it. Oh, we're measuring the frame power, not the byte power. Oh, frame is not enough. Oh. Okay, let me check the frame power. So max P, we also output the frame power by max P. Or we need, we need, this is already corrected. Wait, or are we shifting more than 3 bytes? Let's not shift. Quote works. Okay, let's try. Okay. Oh. Oh, peeps. I didn't fix that one. Not decode byte, but not decode byte old, but get frame power. Frame power doesn't work like that. We could try to fix frame power for now. Nah. Okay, find sync. frame power. This is our frame power, which will be times raw p plus pi plus this, and we only need that, and this is times 4 plus 640 minus 64. Because we want the first and the last bit of the 10 bits. Okay, frame power is now fixed. Let's try again. Okay, sync and decode. Ah, it died. Why? What's going on? What didn't you like? Huh? J, P, J, we know all these things. What's the error? Oh, constant. Okay. Okay, connect. This will be successful. I see it coming. I see it coming. This will be successful. Okay. I'm recording. Sync and decode. Oh shit, didn't work. Okay, let me check if using that somehow changes things. Hey, why? Now it's all over the place. I destroyed it. Wait. Sync power. Zero. Huh? Why is it completely broken now? The only thing that we actually changed is not adding this here. There is 390. Huh? Okay, let me test that with the new frame power. What? Okay, correction, sync correction works except for the 10. What? Ow, why? Is there some noise? Why did this happen? Other than that, it's perfect. Okay, Let me fix plus minus like +6, but this is very compute heavy. Let's retest. Sync and decode. Ah, now it's completely broken. It's all over the place. I missed the sweet spot. That's too much. That's too much. It's half a wavelength. Oh no. Okay. Let's try again. Now it's broken. Why is it broken? Oh, it's at the end? No. Huh? Why does it break here? Huh? Why no more? Why no more data? Hey? Ah. Huh? It's broken. Skipping the ADC and do the measurements in the digital domain using interrupts like frequency counter, just detect the edges. Yeah. The issue, what I see is that you have edges like these here, where the direction is flipping. Also, we have a drift in DC offset, so it won't be that easy to do this. I mean, there's something going on. We could... Let's do the edge counting. Active rectifier. Active rectifier. It sounds like too much work to do the hardware. I want to do it in software. If we can do it in software, in hardware, then we can do it in... Yeah. Schmidt trigger. Let me put something on because it's getting cold in here. It's getting cold in here. Oh, look what I found! Ha ha ha! Booster! Oh no, I'm still recording. This BS won't make it into my video. Schmidt trigger. If you want a filter, we can do a filter. If you want a filter, we can get a filter. If you want a filter, we can get a filter. We do the filter live. Let's do it live. Ah. Jan de Boer. Hi everyone, it's my first time here. What are you looking at? Oh yeah, this is a playback of this micro cassette recorder. We read in the data with the ADC and now trying to we are trying to interpret the data that we stored before on the tape. And it's harder than it looks like. Wagon loads, where do I store the complemented pair? Where do I store it? I have only one channel. I can't store complex numbers on the tape. I could do phase and one right after the other. Yeah, but there is no like instant flip of the waveform. Do you mean like, I mean, if there is noise, the noise affects it at a different point of time. If you look at here, this noise or this noise here, if we store like one wavelength of that and then the same one inverted, yeah, that doesn't work. Sorry. This is not like if you have this DC shift. Look at this. If you have this DC shift here and then the next wavelength you have a different DC shift, then your A and B won't be complementary. There will be completely different A and B's. Same with the noise here. Let's try something else. Let's try filtering the data. I'm curious because we can filter everything that we get. Wait, the code. Read loop, raw value, and let's do filter raw value. Okay, let's do filter here. Function filter value and then return. Schmidt trigger needs a state. Okay, so we have like, oh, that's hard. We assume the filter is called consecutively, so we have like here state filter state. Okay. And V is greater than what? What is the value that we, let's say 200, 206. So we have like 50. Then we change the state 1. And if state is, that's else. State is smaller than 50, then state is 0, and then we return state times 255. Okay, so read ADC. We do it in software now. Huh? What is going on? I don't see the values anymore. Maybe it's too high. Threshold is too high. Okay, let's do... let's go... Okay. Somt. Center plus amp. What's going on? Huh? What did it complain about? State, filter state. That's what's complaining about. Didn't notice before. Okay. Okay, retest. Oh, wait. Huh? Didn't we filter? Oh, wait. Here. There is your filtered stuff. Oh, it failed. It failed the... where is the center, by the way? Looks like... It looks like it's alright. Okay, so let me do... The amp is only 10. Let's try again. Oh, what is going on here? But it was able to decode this Schmidt-triggered stuff with our method. It found the beginning. Oh yeah, that's the marking. Yeah, you can ignore the marking here. Interesting. If we shift it, yeah, the data is here. Look at that. Okay, we lost anything past the 8, but 8 is there. Everything until 8 is there. And then it's broken. Funny. Yeah, it's like a simulated Schmidt trigger. Schmidt trigger is only like you need a little bit more to flip the switch, isn't it? That's how it works. Yeah, there is only like a threshold. There is always a threshold range where you need like to overcome that to flip to the other state, and that's what we are doing here, manually. Here, this is this is how it looks like. The symbol gives it away. Oh yeah, but that doesn't help. We need to count the edges, but we can count it. No, I'm not using moving average. I could do that, by the way. We could do that. Let DC 128 DC offset, and then we will do DC offset and the new DC offset. No, wait, that affects it later. So DC offset, this is how a cap would react, equals DC offset times 0. Plus, or let's do 995 plus V times 0.05. So we have now a moving DC offset, like wished here. Retest, boom. Sync the code. Woo! What? What? We got it! What? No way. This is it. Stupid moving average and a DC offset. What? This is the first time it worked. No way, this must be a coincidence. What? Crazy girl. Okay. Why is the chat not updating on my screen? Okay, I mean, your chat will be on display in the video when I take this in. Somehow my chat here is delayed. I'm hearing voices from the off. This is cool. I like it. Peeps, I like that. What we are seeing here, digital realm is my realm. We could also indicate a sync loss when the power is. So something must. Yeah, it's broken. Lol. Okay, we are done. We're done for today. Are we? Are we done for today? Did I write its final stream? Okay, let's try again. Okay, let's try to decode that. Again! It worked again! What? No way! What? This is stupid! Schmidt trigger with moving average. Ah. Yeah, and storing recruit. Ay. Okay. Challenge accepted. No, not storing that, but we can try to store longer periods of no. We not doing quick ends here. Okay, let's do 8 times 256. Let's store that. Maybe we can get a higher density. Now we could count the edges, maybe even. Ay. And I also don't want to display that. Okay. Let's store a longer data set. Then also we need this here. If pop to 0, console log lost sync plus power return. So we will try to decode all the bytes we can get here. Also, this is so cool. I didn't expect it really to work, peeps. This is new. Okay, record test. Now it's recording. Increasing numbers from 0 to 255, where our buffer is only 32 kilobytes, so we can't transfer the whole 255. Oh shoot. We will miss the start. How do we find the start? We certainly missed the start. Do we? Okay. Okay, retest. No. Lost sync. But it looks like... Is this the start? It looks like it's the start. It's actual sync, but it's... Yeah, no, it's in the beginning of... Shoot. Okay, let's rewind. Let's play, because we have a blank phase of the tape, we missed the sync byte. Now we do the rec test. So we get a proper sync here. Hopefully. Fingers crossed. Yeah. We are amped up, peeps. We are amped up. What if we don't use the Schmidt trigger, but we use the moving average to fix the signal? We have one sync pulse at the beginning of the packet. This is just our test, our first test that actually was able to restore 16 bytes successfully. So what I need to do is find a silence part. So basically something where we are sure that there is no audio whatsoever. That should be simple, like a block, and from that block on we need to find the sync byte again and read the next packet. Okay. Is it? I think it's... Uh-oh. What is this? Doesn't look good. Data looks wrong. Huh? Shoot. It's again only silence. Okay, we got something. Sync lost. After 8 bytes, sync was lost. So sad. Thank you, lines and squares. Should we count the edges? We can also count the edges. Displaying this. Oh yeah, let me change that back, since it seems that we are not successfully recording. Let's do 32 and yeah, whatever. 32 times 32. Okay. With a threshold. Yeah, so counting edges. So what we can do as well is basically what the C64 does is counting like the 0 passes. We have 1, 2 during this phase, and what we can do is we can always, so the sync is perfect, we can always stop the bit, like let's see, double the frequency would be like this. Oops. Wait, yeah, like this, so we can start looking for the next pass from after 3/3 of oh yeah, frequency version of Schmidt trigger. Basically yes, but in that case we are also correcting. So if we are seeing a pass here, both waves have a pass through 0 somewhere from here on, and if it's closer or further apart, like if there is like a skew or whatever for whatever reason, then we can start the next bit here. So we have the implicit correction, and then we can decide if we use only one wave, it's 2 to 4, and we have to decide if there is 3 passes. Not great. We could also count how many turns we got. Like if we have like the first derivative, we can count the zeros there. So this will be 0, 0. Second derivative would indicate in which direction it turns. So if we have like one peak per waveform, one top and one bottom peak, we know, okay, this is a 1. If we have 2 each, it's but I think like the 0 passes would be. Hey Basil, we successfully decoded a little bit of data. We had like 16 bytes, consecutive bytes before even. This is where this is with a Schmidt trigger, a software Schmidt trigger. Still doing DSP, yes, unfortunately. But we're trying to try new things, the same things that C64 does. Foo, yes, I can do that. I can do it now. Let me check if it's already. Oh. Let me check if it's cleaned up. README. This is a copy paste, but thank you Basil for that. This is copy paste. CDC code is USB CDC. Yeah, that code base. Okay, but I can. We're not using the serial chip anymore. This is the copy from. Where did we do it? With the supercluster. That had a flash chip on the back as well for the serial PCI Express thing. That was this open repository. No, initialize repository. Wait, what? Pick repository to open. Huh? Okay, let me get in it. It's somewhere else. I'm not understanding what it actually wants from me. Microtape, PC code. Is this the project CDC tape? Yeah, CDC tape. Okay, initialized. submit, publish, public. Tape smasher. Yeah, I've already the uninspired name CDC tape. What I got on this here, bitluni's micro set. So like the data set, but micro tape. So it's micro set. Uninspired as well. I finished the PCB at 2 o'clock in the morning. So yeah, it's published. Fu, I think you will find it on my GitHub. It's the latest repo. And the code is test is the one that we are using right now. Test 2 is the one with the frequency decoding, and this is the filter that we case. Yes, you missed the beginning here. This is the case, 6 by 5 centimeters. I showed already. I have purchased. Where did I put it? Huh? Where is it gone? Huh? Here. I purchased the original with oh yeah, that's all right. This is the original. It has like the silvery, the brown, the black, the beige, and I bought the precise colors from Bamboo Lab for $60. So we have brown for the buttons. Nobody buys brown filament. Brown is so ugly. Then we have the beige. Then we have the silver. And we have some matte black because I ran out of that. And yeah, the best part is about this, I showed it before. If you compare the size, I don't care. I will put it anyways. It's an art project. He probably won't sue me. I mean, he's the dude. The dude is a creator himself. Look at the size comparison. Look at the size comparison. So here, my device will be this size, and the capabilities will be similar. So running from USB. This is the plan. I revealed it. I spoiled everything. I spoiled the fun. What does QT? Quality treatment? What does modern miniaturization? Yeah, but the miniaturization of the micro cassette thingy here. Wait, where is it? This is 6 by 5.5. But this was done in the early 90s already. So I got a broken Sony recorder to get the write and read head from there. And what I want to do, because that was cheaper, broken recorder is cheaper than buying the head, or basically the same. And I got also the small steppers because I don't want gears. Gears are hard to print. I could use a resin printer, but they're always somewhat warped. So I bought plenty of micro stepper motors. We have those stepper drivers that we want to, and I bought all the stepper motors that were available. The problem is they don't have many steps. So I need plenty of micro steps, but we bought like those fancy stepper drivers. Let me get them. Where are there? Stepper drivers here. you convinced me to buy those. Oh, where are they? Yeah. Anyways, yeah. This year we have some that are capable of more than 60 micro steps, I believe. Otherwise, we will just rotate faster. I have some with gears, but they will add to the thickness. So, and no, look at this. This is in like stepper with gears, but this is quite thick. I got pulleys. Okay, here, let's say this, I looked long time for ones that were white, that were, there are flat steppers, but they are too wide, because I don't want to have to put any gears. I will just use one of the steppers at the time to rotate the tape in the right direction. No mechanics needed. It will be just bloop, tape in, play, and be done. So we can build ourselves. We have smaller steppers, even like smaller if we want to. Yeah, but these look promising, and this is basically the same. It looks like it's the same without the gear. Yeah, I think I bought them with and without gear, so I can try micro stepping. I think I paid $20 for that whole assortment of different stepper motors. But where's the one? Here. How did you erase the tapes? The gear ones will have. Hey, Peter. The geared ones have enough shielding in between, so that will be alright. Someone wrote me. Who wrote me? Who wrote me stuff? Oh, ooh, yeah. Okay. Here is the other one. Yes. I mean, they are encased completely. That's like should be no magnetic leakage. Should it? Oh, that will be nice. Oh, I love this project already. So we can throw away this whole garbage electronics that we can't actually control. Not this one. Not this one. This one. This garbage electronics. We can just throw it away and use the head. Yes, that's. Yeah, I will leave one of the stepper motors. Oh wait, with the geared one. Oh, we can't rotate the geared one. Oh no. I didn't think about that. Okay, so we only can use those without gears. That will be a problem, yeah. Or do we engage it in a different way? No. No, garbage electronics. That's not garbage electronics. It's peak electronics. It's working off 1.5 volts at. It is magic, but yeah. No, because it doesn't care. It doesn't matter. It will just spin. The tape will just run faster if you're at the end of the tape. You just need like a constant step through that. Oh wait. Oh, if you run it backwards. No, If you run it forwards, it will be always the same speed. The tape will just move faster. That's all alright. If you run it in the same direction, if you run it backwards, then the speed will vary. But this is an interesting fact. I also would like to record on the front and the back side at the same time and use the tape only in one direction. So the second stepper motor will be only rewinding, while the first one will be the one that's playing actually. I don't know. Who am I to know that here? Precision gears. Oh, yeah, maybe I need to put in gears. That will be horrible. Stupid stepper motors. Yes, you can. This one even has two recording heads, and which are like on a lever that flip. Endless possibilities. It will be interesting to make that from scratch, because it can be magic. How do you erase the tape? Someone mentioned that you need like a specific frequency to erase the tape. Now I'm on the side project here. Erasing tape. Previously recorded, the frequency used for erasing is typically the same bias frequency, which is often between 40 kHz and 100 kHz for consumer audio tapes. What? Erasing head. But where is the erasing? Is it built in this micro cassette player? Because I don't see that there. It must be, because this recording head has like 4 connections. So there might be just one in the front and one in the back. So it's erasing, and right next to it it's recording already. Why the gap? Then record or playback heads, allowing the tape to... Let me check that. What? Low torque to pull the other spindle. Yeah, I don't care. I will assume the drag is good enough. How do I... Wait, this one... Can't look inside this one. This one is working. I can't see that there is any other. Yeah, here is the same. The head has only one field. Can I show this somehow? Try to show you. We need to look through the window. Focus. Do you see that? Shit, wait. Let me do manual focus. Here. This one doesn't have anything. This one doesn't have anything else but just this. It looks also like that one has, we could take that apart, but this is a functioning one. This is the broken one. Wait, I didn't try it yet. Let's try if that is working somehow. Where do we have batteries? Oh, there is a double A. And here is a double A. I have no clue of the state of this double A batteries here. They are also not actual double A's. Oh yeah, that one has a broken. That one isn't rotating at all, so probably here the rubber band is broken. Yeah, we can repair that. Let's open it up and repair it. This one, yeah, this one has two, but it's so hard to not destroy it because we have so many soldered. You can see the heads here. So this one has two heads, and they're basically going down or up, and we can just open it up. Wait. Here, so you can look. It's looking the same. It's looking. Yeah, it's looking the same like the other one. So. There is no magic to it. We can remove that already. Come on. No. Doesn't want to budge. Alright. Soldered well. This can be removed. Let's open this up and replace it with a regular rubber band. Sticky goo. Are we there yet? Yes, we almost are. Ah, okay. Oh, where's my... I saw the screwdrivers recently here. They are in the room with us. Oh, by the way, I also bought the new really sticky print bed for the Bamboo Labs. So I'm hoping that I never have to take care of stickiness on the print bed again. Where are they? Where are my screwdrivers? They're not there. Okay. They will work for a YouTube video. For the duration of a YouTube video, it will be good enough. Okay, I have some screwdrivers, but not the ones that I usually use. My lab is a mess. Finding parts in the socks, yeah. Politician, why will I be good politician? Yeah, camera. We fix the focus for you. We have manual focus and here. Final, yeah, final. Like in the German big German projects, the cost of the project. Oh, there is another one. Oh, there are tuning potties here. Probably adjusting the speed or something, because that's most this is sticky. Oh, there is yet another one. Sony, the makers of the good gear. Here we go. This is like 80s stuff. Look at that. That vacuum here, that's probably for the bass. Okay, let's check. Yeah, the planning. Well, I need to remove that probably. How do we eBay, everything eBay. Can't. Huh? How is this? There is somewhere a screw hid. Oh yeah, there are screw hiddens. We need to open this. How do I remove that? Okay, this will be hard without breaking. There might be a tab. Here there is a spring. This will be hard. How do I attach the spring later? Because we have screws in here. You can't see. It's too dark. I can reach that screw, but okay. I was able to reach that. Ooh! Yeah. Oh, there is also warranty void. Yeah, I also missed those screws here. They are also marked. Okay. Oh, look at this diode here. I like those designs. I was thinking of putting in a flat oh shit. Something's loose here. Yeah, look at that. Here. That one is missing. That's broken. How is this power cable? Yeah, I can't remove this without okay, so look at that. It's gooey and gluey. Now I will never assemble it again. Here you go. We need the proper length. And there are also remains here. To remove the remains. Where is this going? This power cable here. It's annoying. I don't want to destroy that. I would only need to remove the speaker to have full access. Yeah, I can measure the belt length. Yeah, flywheel is not bad. But because this looks like a stepper motor as well. This doesn't look like a DC motor to me. Shit, there is some gunk. Okay, let me measure the length here. We will just order one and then fix that thing. But I really wanted to salvage the recording head. Now what we do, we take this cheap ass Olympus, which is functional, and take that apart. That looks like 12, but it could be also like, yeah, that looks like 12.7 centimeters. could be 12 point. Oh no, wait. From a hard drive. No, hard drive is spinning too fast. 13 centimeters. How's it called? Belt. Let me check on eBay. Antriebsband? No, what is... Yeah, how do you... Antriebsriemen, okay. Okay, let me check. Yeah. Oh, that looks like. But it's only up to 10 centimeters. Maybe 10 centimeters would work because they are flexible. For $5.99 you get a complete assortment. I like that. 100 millimeter. I mean, it costs nothing. I just should buy it and then see what happens. No, they are too thick. This dude might have Antriebsriemen. What's the keyword? Oops. Wow, look at that. You can get everything on eBay. What the F? Doxing myself already? Wait, I need to check. Okay, so we can buy one and I want Standort Deutschland. Because usually... Oh no. Yeah, it's only from abroad. We get only cars. Combustion cars parts. Fuck. Zuletzt aufgerufen. Yeah, where are they from? China. China. Okay, let's try EU. Otherwise, oh well, then it will be... Yeah, it's all from China, peeps. So I can check on AliExpress and get it with choice. Okay, look at that. 50 pieces, choice. Let's just buy it and be done with it. Ah, cookies. Reject. Welcome deal. 99 cents. Okay, we found and it's choice, so it's in 10 days it's here. All right, perfect. Thank you very much. Next. I need to sign in. I just don't want to expose everything. Continue here. As the reject cookies and substitute my own. Okay, buy now. Okay, I will just... Oh, free shipping. I need the free shipping from $10. I will just put it in my cart and then see what's happening. I hoped I will be able to buy it from a local seller, but apparently it's not available. I just need to now put this thing somewhere where it doesn't lose the screws. And in that case, I will use it here. This will be my storage for that. Du findest auch welche in Deutschland. Kannst du mir einen Link schicken? German Electrician. Ich hatte kein Glück. Also zumindest nicht bei 13 Zentimeter. Maybe I wanted too much, like searching for 13 centimeters. So that's what she said. Wait, let me check. We can try again. Shop. Antriebsriemen, Artikelstandort. 10 centimeters might be too short. I don't know if the tension won't. Yeah, they are alright, but 10 centimeters, I believe. I mean, there is some. Oh, 16 bucks. Okay, that's a word. 16 bucks and then. All right. 16. Yeah, these are 6, and that what you found was this name. Yeah. Wait. Standort Deutschland. Huh? 4? We can just buy the precise one pro Stück. But how do you tell them which one is it? 1 millimeter. Huh? Oh, look at that. It says it's Germany, but it's not. This one isn't for sure. It will take ages. 15 Riemen. Is this one with the correct ship? Oh, look at that. Starshop Germany. Okay. Yeah, probably. And now you have to. Oh, it's a German seller. Oh, here. So it's quick shipping. I might just order this set here. 28. It will be enough with up to 18 centimeters. Perfect. I mean, look at this. You can buy basically this old recorders like Sony, like there, for 20 bucks. Put in one of these belts and sell it for 40 bucks again if you're. So nervig, dass ich immer schauen, ob die Impressum haben. Ich hatte auch immer in Lettland bestellt. Yeah, recently I had one from France, and there was like planned shipping was promised arrival time was 3rd of July, and it arrived 12th of July. But by that time I already disputed the and got my money back from eBay. But that's really not my problem. There was no tracking information, nothing. There was a tracking number which wasn't tracking anything, so it wasn't properly shipped or whatever, registered. And so yeah, probably the dropshipper lost some money on me. I even wanted to pay twice the price for the parts to get them quicker from Europe than waiting for AliExpress. But AliExpress arrived a week earlier in the end. So, yeah, I don't care. If someone disguises that it's shipping from China, then it is what it is. Anyways, cool project. We're making progress. Talking much, not doing much of work here. Should we run a test of? Oh yeah. XT60. Lativa. Oh. Yeah, I recently bought XT90 connectors, but the ones with XT90S are really expensive. You can get like from China you can get the XT90 for like 30 cents or 50 cents a piece, but if you want the S version, which has like this additional resistive layer so you don't an anti-spark thing, then you pay like several dollars per piece, which is a lot for my taste. I'm a cheaper. Okay, did we connect already? Does it still run? Because I tampered with it. Okay, record test. We wanted to change a few things. It's recording our test thing. Sync pointer. Foo! What is wrong? Did you check the code and did you find an error? Did you find it? No, the sync byte is alright now. I can show you. Retest. Here, sync and decode. Bam! You're reading the code. Look at that. It looks alright. It looks alright. The first 8 bytes are in sync and we get some good frame data is alright and also this data, but then sync is lost after the 8 byte. All of the sudden, I don't know why. There is some jitter or whatever. Sync is lost. Maybe there is a drift or whatever. Should we not tamper with, let me check again, the filter. Should we Okay, let's do that. Let's only remove the DC, normalize the DC offset, okay? Let's try that. So we will do V minus DC offset plus 128, okay? So this is our new thing. Okay, there is the sync lost. Let me check. No, sync lost instantly. Here. This would be the perfect. This is where we get all the data. Otherwise the sync is lost. In this region, when we do the automatic search, then we are too late. The sync, yeah, it is, and we get also here. There is also a. Oh wait, this is weak. response here. There is certainly some, not even a clock drift. You can see this is the power, which looks nice. We get a good response. Anything above 100 is certainly correct. Even 13 over 50 is correct. But here we got some errors. Clock tower drift. What? Why does it lose the sync here? We could try something else. Okay, this is the correction of the DC offset, but it doesn't look like it's really. Let me change that slightly to 8 and 2. So yeah, that's what we can do, the calculating the passes. The only issue is here when, yeah, that's what I'm doing. Fu, if you check here, this is where we resync it with plus minus 2 samples, and that's added like the shift, and one wavelength, one full wavelength is 32 samples. So the most we can do like is a quarter of the higher frequency, which will be 4. So we could increase that, but yeah, let's do one thing at a time. What did I change? What did I just change? Oh yeah, I did. Oh, come on. Was connected already? Yeah. Okay, retest. Console. Oh, lost sync after 16, but we are recording 32. Can we get more, or is it just end of our? Yeah, I think it's end of our recording, because we are, look at that. This is our recording buffer, and it's just done at the end. Yeah. After 16, we're probably not. Yeah, we can try again. Okay, let's skip a part. Okay. Oh no, that didn't work. We lost the sync. But there should be more data. No, it's working sometimes. But the DC offset, I don't know. Doesn't look like it's working here. 506. Okay, we lose it here. We have only like one sample where we can read the correct values. The frame is also. Why is the frame so high? We should actually measure the correct decode byte. We should try this and use P here. So we sync with the whole byte, not only the frame. So I don't know. that's not helping. Maximizing that, and it's getting really slow as well. This can't be done on a microcontroller. Let me try again. No, sync is lost. Frame was more reliable than this here. It's interesting that the Schmidt trigger is more like no, that doesn't work. We can also do, let's try -4 +5. That feels like trial and error right now, not really proper systematic improvements. I want to count the edges. We have like until nearly science, yeah. Okay, retest. Where's the proper? Hey Sonic! I missed you. Why can I hear the voices of the Twitch chat? Okay, sync and decode. Oh no, that didn't work at all. Yeah, no good. Interesting. Okay, so what is if we do only one sample? Amiga, guys. Oh, nice. Retests. Yeah. Just need to do the other way around. The method that I didn't try yet. That is one that will work. Okay. Look at that. Only accepting only one sample drift. Yeah, that's coincidence. It doesn't do anything. But there is a frame of looks like it's correcting itself. Strangely, the frame. No, wait. Decode byte. Max power. Why is this different? Something's off because we decoding the byte here. I plus J. Oh, damn it. Why didn't you say anything? Okay, peeps. This will now work. This is now from 0. This will be now from 0 to hero. Okay, peeps, look at this. Sync and decode. Bam! Best ever. 20 bytes. We didn't check for stop and stop. We just checked for the data and shifted by consistency. Here, this is the lowest. We had like a really heavy drift here. Maybe I should try one more, but this is the best what we get so far. Gigabyte, 1.21 gigabyte, yeah. Okay, I will try 5 and 4. So this will be slow. And then we will also test play stop. So we have it also might be, oh yes, that just works. Okay, this is very low here. But that might be the end of the data. Platinenmacher, hello! Guten Abend, willkommen im Stream. So we have some German raiders here on Twitch. Yeah, you just joined, peeps. I hope you're fluent in English because we're doing this stuff in English and you are witnessing a success reading back data that is. Hello Nepertox. Here we are rebuilding a data set here, C64 data set, but with micro cassettes and a micro recorder here. Oh, there. Look, size comparison. This is this big and this is this big. So this was a mini recorder. We made our own PCB that will sandwich there, and we will make a small data set, and now we are trying to decode the stuff that's coming in from the tape, and it looks all right. I think we just hit the end. Thanks for the follow, Pink Queen. Cheat 95. Wo hast du rausgebohrt? Anrufbeantworter? No, this is actually a small, one of super small devices. I have still the case here. Recorder. Here, Olympus. This is the recorder. It's not. It's one of the smallest out there, and I got it for $50. This is the case for it, and we just removed it from the case, the main drive, and attached some wires to the flex PCB. If you look at it right, yes, that are basically those here, but even smaller. So this one is still working. The other one that I got here. What patch? What did you do? Decode byte. What is this? Start bit. Get energy. Resync every byte, but this is what we are doing. Yeah. It's certain. No, it won't be. It won't be here. Here it is. What it will look like. Here, 6 by 5 centimeters. I already started designing it in a 3D printed case with USB, because this is how it will look like. And if you size compare it like with the PCB here, it will be considerably smaller than the original one, and with similar capabilities, maybe not the data density like on the regular cassettes, because that is only mono. And also not the fidelity. See no different side. Yeah. All right. Yeah. What did happen here? Oh yeah, sync loss. Yeah, because we are not sync decode. This is where it starts. Yeah, I think I need to rewind. It's So we have interfaced all the buttons. We can control it over serial here. Okay, now retest, and now let's see. See if we can find it now. It's the wrong position. Oh no, it doesn't sync at all. It's missing the start of the packet. Yeah, this is the start, but this is at the end of the recording. Okay, this is more of it. Oh, right, this works. Look at that. This is probably all the data that we received in 32 kilo samples as 30 bytes. One sync byte, and then that, and it looks, oh wow, the signal strength is so good. This is cool. Let me change something. Phew. I will check your code out later. Yeah, it's doing everything in hardware. There is a Schmidt trigger that's counting the zero passes. We could do this as well. We are doing a more sophisticated approach a little bit by running a DFT on the segments here. Then we can also measure how strong the signal is. So we have here, this is basically, it matches right now because we were recording in 10-bit. Yeah, but no, not really. Cumulative error. Look at this. We have now here plus minus 4 samples is now checked and corrected here. So this is that part. Maybe, you know what, this version works the best right now. I will commit that change and you can check it out. Probably have to merge. Sorry. Better sync with whole byte. Okay. Commit and sync changes. So you will get the latest code, and this is working perfectly now. We can get all the data out. And there is no... What did we change? We had like... Did we just add like more? Yeah. Four samples back and forth. But this is every single byte. Phew. Let me review your code. This is what I'm doing. Like, if you see that, so we skip. We have like each byte is 640 samples. So we're incrementing by these many samples, and then what we do. This is now a bloody hack because we just check before against the frame, which is the start and stop bit, which was a good indicator, but checking just for consistency of the whole byte or whole 10 bits in that case is more like precise, and we are checking that for like plus minus 4 samples, and then picking the displacement that matches the best. Hey Cheat, thank you for the follow. And this is just added to the current position, so it basically corrects up to 4 samples in each direction per byte, which will be per bit half a sample, or like 10 bits is a little bit more, but yeah, this is the maximum drift that we can see. We could do it per bit, which would be interesting, but I think byte might be a better match in that case. We can just, I don't know. The only thing that I would like to do it currently, we are working on. Oh, we are also testing the power with actual DFT. We can do it with our scene table on the microcontroller, but yeah, this is quite a time-consuming part. So I would need to run that DFT in streaming. So maintaining the individual powers in extra array. Oh, this is, wait, this is decode byte. Yeah. Maintaining that power here that we add or test against. No, actually we need to maintain those two values in an extra array, so we can subtract it from the start of the sample queue and add the new value to the end of the queue. This is a little bit of coding stuff. But I see, come on, where's my repo? Vergib mir aber Audio für weitere Codes. Ja. Fuse code. Yeah, okay, let me check. Let's check. Where's the pull requests? Huh? I don't see its pull request. Do I see branch? No. Huh? Wait, Fu, where is your... What the fuck? Wait. I need to find... Because I can't use this stupid chat link. Need to find the streaming window. Yeah, wait. The problem is it's... Pull request, wait. Here we go. Oh wait, this is FSK. Huh? Oh, this is not the one that we are using right now. You did this in the C code. We're not working on the C code right now. We are working in test HTML. This is the one that we use. That the C code is totally deprecated. Let me see. Yeah. Decode byte. start energy. Yeah, this is the problem was like 2 streams ago. Was it Monday? No. Yeah. Did we do it on Monday? Monday we had like the decoding didn't work at all, and there was debugging was really hard because we are streaming the audio from the ADC on the fly. So whenever I paused in the code, yeah, it was gone basically, like the audio. That's why we recorded, like made it transfer only a recording of the audio over serial to the browser and doing everything in browser to figure it out. And once it's figured out, I want to transfer it to C++. But we could actually decode packet. No worries. I'm still interested. Wait, your code is it way shorter? Delay takes period. Did you vibe code it, or did you just hack it quickly? Because I mean, how did you get through this code? Decode byte while true, decode byte sync break, then decode byte return. Yeah, but it will be similar in the end. The only thing that we change is like not running it with like actual sinus, but the sinus table and fixed point arithmetic. Both, yeah. Decode power. Okay, this is the basic sync. Okay, we got that. Decode packet. Decode byte. That's data. Get energy frequency. Where's energy coming from? Where is this coming from? Is there a part missing? Because I don't see decode byte. Yeah, buffer and length is decode packet. Decode buffer I. Is this a state machine? You see, like, get energy frequency. They need to be, but wait, how is the energy Oh, this is the total energy or what? No. Huh? How does that work? I see something missing. I don't know what. Record samples. Okay, this is the old one. And I'm not sure how that's supposed to work if you don't like give it any data or whatever. Get energy and then you're just comparing the frequencies. Is it like reading the ADC on the fly or I don't see get energy. Anyways, this is C code anyways, so let's continue with that stuff. fix everything in. That looks promising. What I wanted to try is, because right now the test recording is using, we are using a different frequency. Maybe we can increase the frequency and store more data in. We can also improve. We can go up to 40,000 here. Also read 40,000 and send 40,000 again. So more samples. Then we will delay microseconds. I think we need to duck enable. Just wait another second to get rid of that tape piece that's not recordable, and then start it. Sample buffer, we can, yeah, whatever, doesn't matter. And then we can record the whole 32 bytes. Okay, I will change that. We will record our test stuff. But I see success here. We can try different things. This resyncing per byte, I just need to streamify it, because currently it's just working on a recording and recalculating stuff all the time, which is not great. Once it's found the sync byte, it should be only doing everything yeah, need to check if we can calculate it in time, because we have only we need to record the samples while analyzing everything, and we have only per sample, when we are recording at 2 kilohertz, no, 2 kilo, what is it, 20, we calculate again, we calculated last time. So it's, let's say 1.5 kilohertz looked promising, times 32, that's 48 kilohertz that we're recording. Alright, see you later, wagon loads. I'll probably be gone in 15 minutes, but yeah, if not, we see each other. Maybe on Monday, if I might stream on Monday again when it's over. Alright, so 38 kilo 38 kilo samples per second, what we are recording from the ADC, and we have 144 megahertz MCU, 48,000. We have 3,000 cycles per sample that we need. This is the most that we should be calculating. So if you're calculating per sample, we can calculate the DFT on the fly and maintain basically the start and the end, like I told you before. All right. Or we will 3,000 cycles might be all right if you consider that we processing. Okay, if we want to process 600 samples, that might be close. We have only like, what is it, 6 clock cycles, 7 clock cycles per sample if we process it in between recording samples. That's not good enough. We need to do it on the fly then. But what I could do, we can do the following. Okay, so the hard part is we have currently 640. We can maybe reduce it if it's reliable. We can reduce it to lower, but let's assume we have only several cycles per sample here. What we are doing is we have 10 buckets here. We calculate so I don't draw to. Oh shit. Here. 10 buckets. These are the 10 bits. And we have like DFT running. We are running 2 DFTs at the same time. So we are analyzing for this frequency and also for this frequency. Alright. So whenever we receive a new sample, let's say this is a sample here at the beginning, at the end. So each new sample is pushed in here. This is a queue, and old sample is pushed out. So we only running as sinus, not a cosine. Usually we would do a complex number or whatever, calculate like sinus of this frequency in the phase plus cosine in the phase, and then or square root, whatever. But we know that for each bit the waveform is only a sinus, so it needs the perfect match here. So we are maintaining 2 values per sample, which are for sinus low frequency and the sinus high frequency. Oh no, we need to recalculate it because it's shifting also the phase. Damn it. Fuck. It's not good. We can't maintain it like here, subtraction from the sum, and here adding sinus, because the phase is shifting. We would need to do it per bit here. And we can't process that. That's a multiplication that will be on the hard limit. The multiplication on this microcontroller takes probably more than one. No, multiplication is probably 1 cycle, but since we are looking up from the table and also loading the instruction takes already two cycles, we have only 4 cycles for the fetches. No, more per instruction. So each instruction takes 1 cycle more, plus the fetch for the sinus table is 2 more instructions, the multiplication, and then we need to add it. That will be basically on the limit. So either we remove the start-stop bytes, then we win a few cycles, but this will be on the hard edge. Or we do it like I did it before with not taking every sample here, not every of the 32 samples, but only taking the key samples from key positions here, like subsampling, not super, no, anyways, like taking only each second sample to do that. But then we can't tell the drift. Oh yeah, we can. Gyros way. Try to throw a FPGA. Yeah, I don't want to change the hardware anymore. Even though I don't know if you noticed, I put a section with a perf board on the PCB. So if I need to change anything, and there are like 16 GPIOs which can be written and read with a single register write or read, so we can actually put there something on the perf board, but it's not big. All right, so this is, we don't have a moving Goertzel algorithm is probably not big enough. Oh, and we need to do it twice for the higher and lower frequency. Except for this here, we know that this sample and this sample and this sample is 0 on both frequencies. Also, this sample is the same, and the same is here somewhere. So this and this. This is basically like FFT. So there are several. I think what is this? And this minus. I think this one and this one is just negative. So you just invert that. So it's almost like an FFT. We can reuse some samples here, and there might be even, I don't know. Yeah, this also here minus. Yeah, and this is unfortunately. There are possibilities to optimize, but we want function first and optimization later. Yeah, streaming analysis will be really hard unless I pre-record the samples, like I look for silence. Yeah. So what we currently have is a packet, blah 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 packet, and then we have silence. So if we have like our 40K, we can probably make it 48K. We have 64 kilobytes of RAM here, SRAM. I wanted to keep like something for the stack. If we see the chunk, we record that, analyze it, the file. I could put it in Flash, but I would rather want to run it on the fly. If we keep the packet 48 kilobytes, let's check. Oh, if we do like, now we need to record it like that. Maybe we could get away with 4 bit per sample, but I don't think so. This is already hard enough to analyze. But if we record that, how many bytes can we read? Okay, let's assume we have 10 we use 640 per byte. Okay, 48,000 divided by 640. So one packet will be 74. With the sync byte, it will be 74 bytes. If we assume like we have something to identify a chunk or whatever on the tape, we can store 64 byte chunks, and what we do is record a chunk, analyze it, and then record another chunk. Either we leave enough space between the chunks, so there's a trick, enough space here in between, so sleeping here, silence, so we can calculate our start sync signal, and then it will be easier if we have like the start sync signal, then we don't need to analyze everything, each sample. I can run a performance test to see how much time we need to calculate and analyze that, and basically continue with the next packet if we're running like that, or we can just pause the playback here by pressing stop. As soon as we lose a sync, or we know, okay, there's CRC or whatever, we have the 64 bytes, we can even do like this. This has the possibility that if we fail reading it, we can retry a different method, or try like if we see, okay, there is something wrong in this area, we can, I don't know, something more sophisticated, but I don't think so. I will just give up. All right. Yeah, it's 12 o'clock. I'm really happy. Oh yeah, let's run the last test. I think we uploaded it already. Did we upload the new change with the wait time? Yeah. We should be able to record a whole packet. Let's rewind. Okay, now they will start the recording and wait for a second longer before it starts writing the packet. Okay. Let's run the retest. Oh, the retest is probably starting to record too early. Yeah. We need to check that. Wait. Oh, good night, cheat. Have a good sleep. Okay. So wait a second. We need to record samples. We need to delay MS not even longer, like 2 seconds or something, before we start recording the samples. Okay. So let me upload that, because we have too much silence in the beginning. Okay. Device is updated. Oh no, we missed the beginning. Oh, there is another beginning. Sync and decode. Oh, yes! Full packet! What? Oh, and the sync value is quite high all the time. Ooh, everything above 500. Oh, amazing, amazing! We can maybe increase the data density, higher frequency and everything. Alright peeps, quite successful day. We were able to restore data without loss, resyncing each byte, and we have a plan. I will transfer the code, like I will test what's doable regarding the density. We have something that's proven to work. Foo! Yeah, you will get the code. You will get the code. Here we go. No worries. You are never a waste of time. Good code. Working state. This is reliable. I will push it. Foo, I will put it in the where's my excavator fund? Here. 6,000. Oh, what is 6,000? I have now to calculate. 6,000 must be like 8,000. What's that? 6,000 is around about 1.6 euros. Foo. Thank you very much. Excavator is coming. 2.3%. This is crazy. But if this project runs as well as the last one with 1.1 million views, then the excavator is coming sooner than later. I tell you that. Yeah, I earned $3,000 last month from the last video from YouTube alone, which is terrible. A terrible rate for 1.1 million views. But that might bring some spare money for the excavator fund. Alright, I'm very happy. Thank you very much for joining the stream today. It was a blast. The booster woke me up today. Booster. I'm not affiliated, but I love this super cheap energy drink from Germany. Bye bye, Johnny. Good night, Foo. Night, everyone. Night, lurkers. Good night, Dusty. Good night, Sonic.